All right, welcome back to the drive-thru, boys and girls. Hungry? Stop by the deli. Make yourself a bologna and cheese sandwich for only 36 cents on white bread with yellow mustard and pickles. All right, we're into 10.2 today. Space, coordinates, and vectors in space. Things are about ready to get really real because we are now working in 3 space for the first time. So, a couple things. You can imagine that they had to make a decision at the very beginning of this system as to which axis would be which. Okay? So what I've tried to do for you there is to draw a 3-dimensional coordinate system. We use a right-handed system exclusively in our book, and what that means is that we have x as the right hand, y, positive x as the right hand, positive y as the left hand, and then z as the head. So if you can imagine this as a person, this as their right hand, their left hand, and their legs down like that. That's a way for you to remember which one is X and which one is Y. Because what you have to be able to understand is that this thing, it can rotate, and you can have it. You can be looking at it from the top, or the bottom, or the left. So kind of imagine it like a sphere. Okay. So the x-axis, positive, will always be the right hand of our little stick figure. That's the first thing you need to know. Okay, if you can imagine a box that is oriented at the corner of our coordinate system. So let's say we have a blue box. Okay, and we wanted to find the distance from this point to the origin. Okay. Well, what we're going to do on this is we're going to rely on the Pythagorean theorem. So, remember that this is x, this is y, and that is z, based on our right-handed system that we learned on the last page. So we know that we have gone, well, that would make this a negative x, sorry, a negative x, the way I drew it. That's fine, not a big deal. We've gone backwards x, then we've gone out y units. This would be a minus x, and then we have gone up z units. Okay? So, to find the distance, we're going to use the old-fashioned 2-dimensional Pythagorean theorem. Remember, this is a box, so that is a right angle. Excuse me. That is a right angle right there. So if you were looking from above, that triangle would look like this. Okay? And this length would be y. This blue would have x as a length, but minus x as a coordinate. So to find the length of our diagonal of our base, which would be our hypotenuse, we would just do the square root of y squared plus minus x squared, okay, which is the square root of x squared plus y squared. So we leave it like that. So now we know that the red line has a length, radical x squared plus y squared. That's still from our 2-dimensional Pythagorean theorem. Well, now what we have is we have another 2-dimensional right triangle, okay, and if I drew that out, that's what we're looking for. This is one of the legs, and now there's the other leg. So we have z for one of our legs, and the square root of x squared plus y squared as the other leg. We are looking for this distance here, d. So it's going to be the square root of, well, can you see that? When I squared this, that canceled with the radical. So now we have just found that this green line has a distance of the square root of x squared plus y squared plus z squared. And maybe now you understand why our distance formula in 3 space is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. How clean is that? Such a close resemblance to the two-dimensional distance formula if everything was just so simple in 3 space. But you're going to find out, like the equation of lines, the equation of planes, it's just not that easy anymore. But the distance formula works out really, really simple, so it's pretty easy to remember. There are 2 other things that work out really nice. What would you think the equation of a sphere is? Well, if you remember the equation of a circle, the circle are all the points that lie in a plane that are equidistant from a set point called the center. And so you remember that the circle is x minus x1 squared plus y minus y1 squared equals r squared. I hope you understand that the circle equation is just the distance formula. That's all it is. I hope at some point in your math career you've understood that that's all that is. It's the set of all points that are equidistant from a set point, x1 comma y1, a distance of r. Well, now we can just say that a sphere is x minus x1 squared plus y minus y1 squared plus z minus z1 squared equals r squared, where r is our radius and the point x1 comma y1 comma z1 is our center. How cool and clean is that? And finally, the midpoint formula. I hope you can get this one. The midpoint of 2 points, x comma y comma z, and x1 comma y1 comma z1 is the average of the 2 coordinates. Okay, so nothing has changed there. We've just added a variable. So, some of the cool little things that you're going to start discovering. Let's see, we got an example next. We do. Find the equation of a sphere with a diameter that has an endpoints of 1, 2, 3. Remember the right-hand rule. So, okay, over 1, and then out 2, and then up 3. So somewhere over here, it's kind of helpful to like write a little tracer like that. There's one endpoint, and then 4, 5, 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then 6. Okay, so we go down 4, then over 5, then up 6. So there's where that point exists. Okay, so these are the endpoints of the diameter. So somewhere in here is the center of our circle, and our sphere. Oh, what a terrible sphere. That's going to look something like that. Okay. So first we need to find the center Okay, so the center is going to be the midpoint of those, so that's going to be 2.5 comma half of 7, 3.5 comma 4.5, okay? And our radius, let's see, well, our radius is going to be half of our diameter, and our diameter, we're just going to use the distance formula, is the square root of 3 squared plus 3 squared plus 3 squared. So it's the square root of 27. So that's 3 radical 3 is our diameter. So our radius then is half the diameter, 3 radical 3 over 2. So now that we have the center and the radius, we can write this nasty equation as x minus 2.5. Notice that I'm like an anti-math teacher. I'm using decimals and fractions in the same equation because I just don't like to follow that many rules. Okay, r squared, so 3 radical 3 over 2 squared. Oh, 3 radical 3 squared. Oh dear, 3 radical 3 over 2. Alright, so if I clean that up a little bit, x minus 5 halves squared plus y minus 7 halves squared is equal to did I do that right? I think so, but Kevin will tell me. Alright, so parallel vectors in 3 space. Here's something that's important to know. That vector is parallel to that vector. Okay, so even though they are traveling in a different direction, since v is -1 times u, then v is parallel to u. Okay, so any scalar multiple will do. It doesn't have to be an integer. So for example, if w is equal to and let's say v2, because I'm running out of letters because I'm not very creative, is equal to -2 comma -3 comma -4, then w is parallel to v2 since w is -2 times v2. So that's how we can tell if vectors are parallel. Example 2. So we got P, Q, and R. I'm not going to draw a picture for this because we don't really need to. Determine, okay, so how can we figure this out? Well, we've got this vector PQ, and then imagine this vector PR. Okay? This picture either looks like this, or it looks like this. Can you imagine that? That's what we're trying to figure out. So, we know that PQ is, Q is the terminal point, don't forget, so I've already messed this up once. So, we got to do terminal minus initial. So 2 minus 1 is 1. 1 minus a -2 is 3. 0 minus 3 is -3. So I believe that is PQ. Okay? PR is 4 minus 1 is 3. 7 minus a negative 2 is 9. And negative 6 minus 3 is negative 9. Okay? So, since PQ is parallel to PR, and both vectors contain point P, then you know this is the scenario that must happen, and PQ and R all lie on the same line. Again, because they're parallel and share a point. When we start to define the equation of a line, that's going to be an important concept. Alright, example 3. Find the terminal point of vector V given its initial point. This is one of these questions that dupes you into thinking that you're back into 2 space. But keep in mind, V is really 3I plus 0j, free OJ, plus 6k. Okay? Alright, so find the terminal point. So we know the vector. We know that the vector is 3, 0, 6. So this vector, if you wanted to just sketch it real quick, goes 1, 2, 3, right 0, and then up 6, 2, 3, 4, 5. So that would be like somewhere here. So this vector is in the XZ plane. It's in the XZ plane, which is a plane you guys have never ridden before, but it's a good ride. Okay? So, its initial point is negative 2, 4, 5. So remember, in 2 space, we decided that vectors have no position. This vector could be somewhere way over here, out in space somewhere. But when we write it, okay, when we write this vector, we kind of copy it and move it into its original position starting at the origin. So that's what's happening here, okay? This is what the vector looks like when we started at the origin, but it didn't start at the origin, it started here. So we just got to kind of use some problem-solving strategies. So we know that this is going to be terminal minus initial. Let's not screw that up. So x minus a negative 2, comma, y minus 4, comma, z minus 5 is equal to 3, 0, 6. So there is some point x, y, z that we used along with the initial point negative 2, 4, 5 in order to determine the vector 3, 0, 6. So now I've just got 3 separate little equations to solve. X minus a negative 2 equals 3. Y minus 4 is equal to 0. And z minus 5 is equal to 6. So the initial vector must be, let's see, that's x plus 2, so 1, 4, 11. And if you pop that in, you better get the right, and yes, indeed, you do. I believe that is the end of the lecture. Boom!